Hi everyone, here is a quick video on P2 proof where I will go through some of the exam questions that popped up over the last couple of years. Before we start, I would just like to go over the strategy that we might need for some of these questions. For example, this first question here. If A is greater or equal to B, then I can say A minus B is greater or equal to 0. So if we can show that A minus B is greater or equal to 0, then A must be greater or equal to B. So that's kind of the strategy I'm going to use in these sorts of questions. So let's start and look at I, where it says x minus 4 squared is greater or equal to 2x minus 9. So I'm going to use this strategy and I'm going to rearrange it so that I have 0 on one side. So I'm going to get x minus 4 all squared, subtract 2x minus 9, which is greater or equal to 0, and then I expand my brackets, x squared minus 8x plus 16 minus 2x plus 9 greater or 0. I now simplify this because remember I want to get to a point where I can show that A minus B is greater or equal to 0. So I'm aiming to get there. So I'm going to simplify this and I get x squared minus 10x plus 25 greater or equal to 0. And hopefully you can recognize that I could factorize this and it becomes x minus 5 all squared greater or equal to 0. Now you know that a square number is always going to be greater or equal to 0. So we have proved here A minus B is always greater than 0. We've just proved that by ending up with x minus 5 all squared. Therefore, we know our initial statement is true. So we just need to go and write a summary here. Write a little summary. As x minus 5 squared is always greater or equal to 0. And we could say for any real value of x, therefore x minus 4 all squared must be greater or equal to 2x minus 9. So that there is how we deal with I. The second part, show that the following statement is untrue. 2 to the n plus 1 is a prime number for all values of n, where n is a natural number. So all we need to do there is we need one counterexample, just one counterexample, so we can show that that statement is not true. I'm just going to move over there. Let's have a look at that. Double I. So we need one counterexample. You don't need to write this down for the examiner, but I just like to write down what we're trying to do here. So, for example, if n is equal to 3, then I know that 2 to the 3 plus 1 is equal to 9, which is not prime. Therefore, and we can go back to our original statement, 2 to the n plus 1 is not a prime number for all natural values of n. Therefore, 2 to the n plus 1 is not a prime number for all values of n. Okay, so that is how we deal with those two parts of this question. In this question, it's very similar to what we've done previously, to the previous question. All we want to do is we want to rearrange the statement so that we show that A minus B ends up being greater or equal to 0, and therefore we can say that our initial statement, A greater or equal to B, must be true. Because remember, we are kind of starting, we are deeming this to be A greater or equal to B. So let's write this out. 3x plus 1 greater or equal to 2 times root of 3x. So remember, I want to end up with something which is always greater or equal to 0. So essentially, I want to end up with a square number. So in order for that to happen, it's going to be useful to square both sides. And I'm going to subtract my right-hand side squared. Then I'm going to simplify this, which will give me 9x squared plus 6x plus 1. Subtract, well, 2 squared is 4, and root 3x all squared is just root 3x, so 4 times root 3x is 12x, which is greater or equal to 0. This then will simplify to 9x squared, take 6x plus 1 greater or equal to 0, and there I can factorize this into 3x, take 1 all squared greater or equal to 0. Again, I need to finish with a conclusion. You must have that conclusion. Something in the line of square numbers are always, right, greater or equal to 0. Therefore, 3x minus 1 squared is greater or equal to 0, and therefore 3x plus 1 is greater or equal to 2 root 3x. That was the first part of this question. Following part, I said, show that the following statement is not true. That means we just need one counterexample. The sum of 3 consecutive prime numbers is always a multiple of 5. So let's have a look at if we pick 2, 3, and 5. Two, 3, 5, obviously that's going to sum to 10. The next consecutive prime numbers, 3, 5, and 7, sums to 15. So we've got then 5, 7, 11, which adds to 23. And there we go. We have found one counterexample to prove that the sum of 3 consecutive primes is not always a multiple of 5. In this question, we are asked to prove that for all single-digit prime numbers p cubed plus p is a multiple of 10. So the single-digit prime numbers 2, 3, 5, 7. There we go. Those are the first 4 primes and all the single-digit primes. So let's go and prove that this statement is true. When p is equal to 2, I get that 2 cubed plus 2, that's 8 plus 2 is 10. When p is equal to 3, I get 3 cubed plus 3, 27 add 3 is 30. When p is equal to 5, 5 cubed, 125, plus 5 gives me 130. And when p is equal to 7, I've got 7 cubed, add 7, so that's 343, add 7, which is 350. All cases, therefore, give a multiple of 10, therefore proved for all single-digit primes. Remember, this conclusion is really important for the final mark. So let's have a look. That was part I. Part II. Show using algebra that for any value of n, natural number, n plus 1 cubed minus n cubed is not a multiple of 3. So we're going to start with this, n plus 1 cubed, take away n cubed. So we want to show that we do not get a multiple of 3. And remember here that a multiple of 3 can always be factorized in such a way that 3 is a common factor. So if we can show that that's not the case, so for example we get 3n plus 1 or 3n minus 1, then we have proved that that statement. So let's expand these brackets. n plus 1 all cubed, so I'm just thinking about my binomial expansion, 1, 3, 3, 1. So it's 1n cubed, 3n squared, 3n, and 1. So this is going to become n cubed plus 3n squared plus 3n plus 1, subtract n cubed. So I can take away my working out here. I then simplify this. n cubed take n cubed cancels, so I'm left with 3n squared plus 3n plus 1. And if I then factor out 3 from the first two terms, I will end up with 3n squared plus n plus 1, which is one more, which is one more than a multiple of 3. So we have proved that n plus 1 cubed minus n cubed is not a multiple of 3. So this question, the final question we're going to have a look at, very similar to question 1 and 2. I have a statement A is greater or equal to B, and if I can manipulate it and show that A minus B is always greater or equal to 0, the difference between A and B will always be positive, then it makes sense to say, well, therefore A must be greater than B. So that's all I'm going to do here. I'm going to start by writing out x plus y over 2 greater or equal to the root of xy. And I'm just going to multiply throughout by 2, so I'll get 2 root xy. I then recall I want to write it in the form of a square number because we know that a square number, we want to show that we get a square number here because we know that will always be greater or equal to 0. So I'm going to rearrange this to get x minus 2 root xy plus y greater or equal to 0. This is my middle term. So if I were to think of putting this into brackets, squared greater or equal to 0, then my first term, in order to get minus 2 root xy, right, that had to be minus 2 times root x times root y. And in order to get that, well, then my first term must be x, because x squared, my first term must be root x, because root x squared is going to give me x. My second term in the bracket must be root y, because root y squared will give me y there. So this, and in order to get my minus 2xy, it's got to be at negative root y. And I have therefore factorized this expression. I know that root x minus root y is always greater than 0. Therefore, x plus y over 2 must be greater or equal to root of xy. We need that final statement conclusion there. So, final part of this question, part B. Prove by counterexample that this inequality that does not hold when x and y are both negative. So let's have a look at this. So for a counterexample, I just need one example that doesn't work. So let's say x is -1 and y is equal to -2. Well, then x plus y over 2 greater than root xy will become -1 add -2 divided by 2. So that gives me -3 over 2. And root xy is equal to root of 2. And I know that -3 over 2 is not greater or equal to root 2. So there you go. We have proved this inequality does not hold. Therefore, does not hold when x and y are negative. So that's it. Those are the 4 proof questions. I wanted to have a look at that. I hope that was useful. Let me know if you have any other questions you'd like me to work through with you.